All right, if you feel comfortable with it, go ahead and try example number 2 on your own. It's this one right here. I'm going to walk you through it. All right, we've got 12.00 grams of CH3NO2. It's combusted according to the reaction above, and we end up with 69,700 joules of heat being released. Remember, that means it's a negative number. In this case, it wants us to calculate the enthalpy of the reaction in kilojoules per mole of reaction. So this may seem a little tricky at first, and it's a little different than anything we've done before. But I think you can handle it. Let's start by what we definitely know we need to do. I have grams. I cannot use grams in stoichiometry. I have to turn it into moles. So the CH3NO2, I'm going to start with that. That's my given compound I'm going to be using. I have 12.00 grams of CH3NO2. I need to try to find the number of moles that would be. So 1 mole of CH3NO2 is equal to 61.044 grams, just using the periodic table to find the molar mass. Don't forget, you're always canceling out your units in dimensional analysis. Trying to find moles, we end up with 0.1966 moles. And that's what I'm going to be putting on the top of my reaction. 0.1966 moles, and of course the bottom in our denominator we would have 4 moles of CH3NO2. All right, the other information that we've been given is the number of joules of heat that's released. I notice right now that this says kilojoules per mole, so it would be a good idea for me to go ahead right now and turn that heat into kilojoules. So the heat that we're dealing with is negative, remember it's released, so that's negative 69,700 joules of heat. What would that be in kilojoules? We'll just move your decimal over 3 places. It's negative 69.7 kilojoules. Well, that gets us started. That gets us set up. Now we can go ahead and solve for what we're looking for. My unknown is actually the heat of the reaction. This is kind of weird. The unknown is on the bottom. X kilojoules. Because I've got negative 69.7 kilojoules. That's what's produced when I combust 0.1966 moles of CH3NO2. So that's the reason that those two values are both on top. This is the amount of heat that's produced when we burn that much CH3NO2. I'm going to get rid of that to clean it up a little bit. So now we're just going to set up the proportion and solve for x. It's just that x is on the bottom this time. That's the only real difference. So we have 0.1966 moles of CH3NO2 over 4 moles of CH3NO2, because there are 4 moles in the reaction, and I want to know how many kilojoules are in a mole of the reaction. And then I'm going to put negative 69.7 kilojoules divided by x kilojoules. Cross multiply, rearrange, you're going to end up with x being negative 1,418, which after rounding to 3 sig figs is going to be about negative 1,420 kilojoules. So what that means is delta H of reaction is negative 1,420. Our units would be kilojoules per mole of reaction.